Welcome to Next Gen Manufacturing. Today, we are diving deep into the world of supermaterials. You know, the stuff that's making everything around us lighter, stronger, and, believe it or not, way more sustainable. So, how do you do it? How do you make something that's both incredibly light and unbelievably strong? I mean, think about it. A high-performance race car, a cutting-edge aircraft wing, one of those huge wind turbine blades. The secret sauce? It's not just the design. It's the material itself, and crucially, how you actually make it. All right, so the hero of our story today is this stuff, Continuous Long-Fiber Thermoplastic. We'll just call it CLFT, because that's a mouthful. And look, this is not your everyday plastic, not even close. What we're talking about is a supermaterial. You've got these long, unbroken fibers, think carbon or glass, that give it incredible strength. And they're embedded in a special plastic that you can melt down and reshape. So today, we're going to get into the really clever ways engineers are turning these materials into the products of the future. Okay, here's the game plan. We'll start with how these supermaterials are even made. Then we'll look at the cool processes for creating different shapes, from straight beams to hollow tubes. After that, we'll check out high-volume molding, and finally, we'll tie it all together and see why this is such a huge leap forward. All right, first things first. Before you can shape anything, you have to actually make the material. And the whole name of the game is getting that plastic to perfectly, and I mean perfectly, coat every single one of those reinforcing fibers. And you know, there are a few pretty smart ways to do this. You could dissolve the plastic and just soak the fibers in it, or you could dust the fibers with a fine plastic powder, kind of like powdered sugar. But one of the slickest methods is called commingling, where you literally weave the plastic fibers and the reinforcing fibers together right from the start. But look, no matter which way you do it, the goal is always the same. You've got to get that perfect, intimate bond between the fiber and the plastic. That's the foundation for everything that comes next. Okay, so we've got our material. Now, how do you make those long, continuous shapes? You know, things like beams, or pipes, or even window frames. Well, the answer comes down to two really key processes. Let's start with pultrusion. The name kind of gives it away, right? It's the exact opposite of extrusion. Instead of pushing material out of a die, you are pulling it through. The analogy is perfect. It's like making spaghetti, where you pull the dough through a shaper. Except, you know, instead of pasta, we're making incredibly strong structural beams. So here's how it works. It's basically one long, continuous assembly line. You start with these big spools of CLFT called rovings. They get fed into an infrared oven, which melts the plastic. Then this big, powerful tractor unit grabs the material and just pulls it through a series of heated dies that squeeze it and form it into the exact profile you want. After that, it gets cooled down in a water bath to solidify, and a saw at the end just chops it to length. It's amazing to watch. Spools of fiber go in one end, and a perfect, solid beam comes out the other. Now, there's a little twist on this called pull extrusion. It's basically the exact same thing, you just bolt an extruder onto the end of the line. Why? To add a final outer layer or a jacket for things like color or UV protection. Simple, but effective. Okay, but what happens when your fibers aren't all lined up in one direction? I mean, what if you're working with a woven fabric where you need strength in multiple directions? For that, we turn to a different technique, one that's actually borrowed from the middle industry, roll forming. So with this method, instead of pulling spools of fiber, you start with a flat sheet of that CLFT fabric. You heat it up until it's pliable, and then you feed it through this series of custom-shaped rollers. Each set of rollers bends it just a little bit more, gradually folding it into a complex shape, like a C-channel. What's interesting is that it uses way less pressure than metal roll forming, which is great because it doesn't damage that woven fiber structure. All right, so that takes care of straight lines and open shapes. But what about hollow things? How do you make something like a high-pressure tank, or a pipe, or even a super lightweight, high-tech bicycle frame? That's a whole different puzzle. Well, one answer is a really elegant process called filament winding. Seriously, it's like wrapping a present, but instead of paper and tape, you're using a robotic arm and heated ribbons of super strong composite material. It's precision engineering at its finest. So you've got this core shape. It's called a mandrel, and it's spinning. A robotic arm then takes this heated ribbon of CLFT and just wraps it perfectly around the mandrel. As it's wrapping, either a pressure roller or even a little flame torch follows right behind it, melting and fusing the layers together on the fly. And here's the really cool part. By changing the angle of the wrap, you can go almost straight or in a tight spiral, engineers can literally dial in the strength exactly where it needs to be. Okay, another really clever way to make hollow parts is called bladder molding. And the best way to think about this is like building a ship in a bottle. The bottle is your metal mold, and the ship, well, the ship is the part you're trying to create by inflating it from the inside out. Here's how it works. You take sheets of CLFT fabric and wrap them around a flexible, inflatable silicone bladder. Then you stick the whole thing inside a heated, two-part metal mold and close it up. Next, you pump hot air into the bladder. It inflates, and bam! It presses that fabric hard against the hot inner walls of the mold. You let it cool down, deflate the bladder, pull it out, and what's left is a perfect, hollow part with a super smooth finish inside and out. Okay, let's get to the big one. High-volume production. How do we crank out thousands or even millions of complex parts for something like the auto industry? This is where molding comes into play. First up is thermostamping, and this is all about pure speed. It's pretty straightforward. You take a sheet of CLFT, heat it up, stick it in a high-speed press, and wham, you've stamped it into its final shape. We're talking a matter of seconds. It's fantastic for things like structural panels and body parts. But honestly, the real magic is a process called co-molding. This is where you really get the best of both worlds. Imagine this. You take a super strong CLFT piece, this is going to be the skeleton of your part, and you place it inside an injection mold. Then, you inject a regular flowable plastic all around it. That plastic forms the skin, the little clips, the ribs, all the complex details. So what you get in one single step is a finished, complex part that has this incredibly strong, targeted reinforcement right where you need it. It's a total game changer. So with all these cool processes, you might be asking, why is this such a big deal? Why is it so revolutionary? Well, the answer really jumps out at you when you look at the data. This is where you see the true next-gen advantage. Just take a look at this. It's a massive jump. Down here at the bottom, you have your standard plastics. A step up, you have plastics with some short fibers mixed in for a bit more strength. Better, for sure. But then, look what happens when you use continuous long fibers. The performance isn't just a little bit better. It's not even in the same ballpark. It is in a completely different league when it comes to strength and stiffness. And this table just lays it all out, perfectly showing the advantage over older methods. The next-gen thermoplastic processes, they are dramatically faster, they don't give off nasty volatile emissions, so it's a much cleaner, safer place to work. The raw material can sit on a shelf forever. But here's the kicker, and this is probably the most important point of all. The finished parts are fully recyclable. You can actually melt them down and make something new. That right there is the definition of sustainable manufacturing. So that's really the heart of it, isn't it? Faster, cleaner, stronger, and recyclable. This isn't just a small step forward. These next-gen manufacturing methods are a fundamental shift in how we make things. We can now create products that are not only high performance, but also responsible. So the final question really is, now that we can build with these recyclable supermaterials, what are we going to reimagine next? Think about it. Lighter cars, more efficient planes, infrastructure that lasts for generations. The ability to manufacture like this just blows the doors wide open for design and innovation. The possibilities, they're really just starting to unfold. Thanks for watching.